actually. So we'll go very quickly through them in terms of just being able to show you the research that we've done on an on-body ergonomic lifting aid. We know that not all jobs are able to be automated, and so and sometimes it's just workers often lift without ergonomic aids, as you said before there, Jessica, just because it's just faster than it is to do something else. And then sometimes some workspaces are just too small, so you can't always perhaps lift in the proper way or use assistive devices. So in terms of on-body ergonomic aids for the back, a lot of people have been trying to sort of solve this problem for a long time. And some of these devices actually would work, and others I would really question whether or not they would able to work. But none of them ever made it to the workplace, simply because of either the look of them or the fact that they weren't well designed. What we're going to look at today are a number of different lab studies, and I'll help keep track of them as we go along, and a couple of field studies on this ergonomic lifting aid. And our particular model of testing was usually lifting without such a device and then lifting with the device. So that's a typical protocol that was used. In terms of the first study, my colleague Mohammed Abdulli from Ryerson University was the one who sort of got the ball started, and he was taking a look at the typical posture of lifting. And if you're lifting anything, whether you're bending your knees or not, you're only using your back muscles to try and bring your body weight and the load back up to a standing position. But if you were able to get some sort of elastic element in the system, you could actually have a longer moment arm and therefore be able to use an elastic element to counterbalance the body weight and the load. And so if you work that out mathematically and just put it in Excel, you can actually get the kind of proof that we would get empirically. And you're going to get an added an amount of torque because of the assisted device. It's going to apply a counter moment against the pelvis, which is quite withstandable, and mathematically you can reduce the compression and the shear forces based on what you're looking at. So that got the ball started. And in terms of just using the developing software, we were using something called the Hoff Model, which is looking at the distances from this from the lower back in terms of to try and look at the moments, and then we did a dynamic model through using visual Nastran. So we were just comparing the two to make sure that our software was correct. Unfortunately, I don't have the movie's older, so it didn't actually fit into the new system, but this fellow was going to actually lift for you. He isn't going to do it right now on the screen because I haven't got it loaded. But you can see that he's quite well instrumented here in terms of the subject. We have a number of different studies, and rather than talk to you about each one of them, I'll just sort of go over in a blanket way the different technologies that we were using. In this case, we were using electromagnetic sensors to look at the body position and mathematically making calculations based on the lower back L4, L5 joint, what the moments would be because of the posture and the load that he's lifting. In other cases, we were using Optotrak LED sensors in order to get the same information, a force plate in some cases and a link segment model in other cases. The people were also instrumented with strain gauges when we were using the PLAD, personal lift assistive device, in order to measure the force contribution by the assistive device, and then subtract it from the body situation. We were also using electromyography. These are the back muscles, the lumbar erector spinae and the thoracic erector spinae, as well as the external obliques and the rectus abdominis. And these were normalized to 100% of maximum contraction, and we were either integrating the EMG or using the RMS signal of the EMG, depending on the situation. We also had to have switches in the system so that we could look at the timing and synchronize the various systems together using switches on the box. So depending on the study, those were the levels of complexity. And here you can see the instrumentation on the person, the EMG position of some of the sensors, as well as the maximal effort contractions that we were using. So in the first instance here, I'll just tell you about the results of loads, effective load, and integrated EMG. And so this time he has the first generation of the lifting assist device on, and he's going to lift this box and put it up onto this shelf right here. This is then the visual Nastran version, and it will work, I believe, that one. Let me get the mouse over there. So you'll at least be able to see what he did, although I can't show you the other video because it's an older video. Anyway, so our outcome variables were then looking at the moments on the back, PLAD versus no-PLAD, and the integrated EMG signals of the 4 various muscles. And we had lots of different types of studies. We looked at different genders, we looked at different loads, we looked at different styles, or we looked at different orientations, meaning symmetric or asymmetric. So here's, oops, sorry, the cursor was over there. Okay. Loads. These are your male data for your females. The PLAD in this case is the PLAD is always the lower one in terms of the either one of the 2 genders, and you can see that regardless of the load lifted, the PLAD data was showing a reduction in the back moment across the different lifting loads. This is also true for the women. Different numbers, but still the same concept. This was also true whether we were looking at asymmetric. It was also true whether we were looking at lifting styles, stoop or squat, or freestyle lifting styles. So this represents all of that. When you look at the EMG signals that were coming from the back muscles, this is your lower back, this is your thoracic erector spinae, and these are your abdominal muscles. Regardless of whether you were looking, the green here in this case is the lift assist, and the orange is the lift assist in this case. So in all of those cases then, for the back muscles, you would see a reduced moment, or reduced EMG activity, depending on the sample that we took. No effect on the abdominal muscles per se in that regard. And so the erector spinae activity levels were reduced anywhere from 14 to 27% based on the conditions that we were looking at. So the next series of studies that I will report is looking at the lifting fatigue. And so in this particular case, our outcome variables were the amplitude, the frequency of the EMG signal, as well as subjective perceived exertion and heart rate. And we made our measurements during a back strength test, not during the actual lifting task. So if I flip to the next slide, again, my videos didn't work here, but this person is lifting at a rate of 12 reps per minute, and he's lifting for 45 minutes, which is a lot of lifting in a very short time. And then he was interrupted every 5 minutes to pull against this load cell. And so he pulled with 50% of his maximum voluntary contraction and tried to keep that 50% within a line. And that's what we use to do our EMG analysis for fatigue analysis. So if you take a look at this, is the thoracic RMS signal during that static test. These are our young researchers who are involved in it. And this is the PLAD data here, and here's the amplitude of the signals from the erector, from the lumbar, and this is for men and this is for women, of the thoracic area. And you can see the dramatic reduction in EMG requirement during that lifting task. This is the lumbar area. Again, PLAD, no-PLAD. This is PLAD, no-PLAD. And regardless of being men or women, you still had that same reduced need for EMG activity. This is the psychophysical response, and the task is very arduous. We, in terms of what they were doing, and so, the RPEs went up regardless of whether this is the PLAD situation, this is the no-PLAD situation. So regardless, they went up, but you can see they're very close together, as much because of the difficulty of the task. And heart rate was more or less responding in the same way. I have a later slide that will show you the heart rate responses. But, there's definitely a difference with time, but not necessarily a difference with device that's of any great drama at this point. But I would hypothesize that it's mainly because of the arduousness of the task. now we're going to take a look at the safety, and we were trying to evaluate safety from a number of different standpoints. One was what was happening with the technique as the person did their lifting. And so the load conditions, we actually had no load and then 10% of max back strength. So here's your back strength test. You pull against a load cell, and then we set the load in the box at 10% of your maximum back strength in this particular case. And we were using a different technology, the Optotrak, to actually collect the data, and then we had the person do a number of continuous lifts. So that's the protocol. And the first way we looked at this with lifting technique is we basically did a principal components analysis across the 30 lifts in each particular case. And we're able to see a definite difference. This is PC1, I believe, in terms of the no-PLAD and the PLAD circumstance. So when we kept with a lot of PC scores, being able to explain 88% of the variance in the data. And what was interpreted when you looked at it is these particular scores showed that we had less lumbar flexion and thoracic flexion, meaning the back was straighter, and significantly greater hip and ankle flexion, which means basically they're bending more at the knees than they are at the back with this particular device. We also took a look at dynamic spinal stability. So this is sort of discussing, what are we talking about? You have a passive subsystem. We have the muscles that are sort of involved in an active system, and they will create a certain amount of spinal stability. And if we don't have spinal stability, it'll cause perturbations or control errors, which can lead to back pain. So if we actually look at the process that Ryan was using, he was using Lyapunov system analysis. And so this is the 30 different lifts that you see. So they're not perfect in terms of a sine wave. There's a bit of variation in them. And if you actually plotted them, you'd see the variation that is occurring. In terms of comparing the two devices, we had, if you have a lower score, it's actually better in this regard. And so when we're looking at the long-term component, no difference. But if you looked at the shorter-term variation, sort of down in these changeover areas, the PLAD actually improved the dynamic stability and reflected a more stable neural muscular control over the trunk motions. So from those two studies, we are believing that we're not going to add risk if you're adding an assisted device of this type. We then took a look at different tensions that you might have in the device in both the back and the legs. So we're using EMG in these cases. And so you see your typical response. If I have more help, my muscle activity is going to be used less. So this is your thoracic area, your lumbar area. This is no PLAD here, and this is various tensions in the PLAD. And you can see that if we help you more, you're using your back muscles less. All right, so that's just looking at a tension effect. But what was interesting is we had some significance over here in the leg muscles, and that was worth exploring further, simply because here's the one with no PLAD. It's actually the least in our legs, and we're asking for more work in our leg muscles, as we increase the tension in the PLAD. Okay, so then we went ahead with a protocol that was going to look at EMG, but it was also going to look at energy demand. So far what we've done is proven that if I have assistive device, I will help, the worker will have less work to do on their back. What some employers might do, or what workers might do, is actually work harder. So they're keeping a sort of a homeostasis, and because their back has to work less hard, they do more lifting, which is a real problem. That wasn't the intent of the assistive device. And so we got a metabolic cart. We used EMG as well as position sensors to try and sort of look at this particular problem. So again, they're lifting 10% of their back strength. We're making sure the heart rate is back to baseline before we do any more work. We measured oxygen consumption continuously as well as various EMG signals. So here's your MVO2 across the two scenarios. It hasn't changed, which in my opinion is good. It's telling companies and researchers, that if you use an assisted device for your back, it doesn't mean that you're going to use less energy demand. And, So this is what this is saying. And in terms of looking at the differences between the PLAD, no-PLAD conditions, leg muscles were being asked for more work. So despite the fact our back is being asked for less work, our leg muscles are being asked to do more work. So the person still feels tired, the same tired, just tired, more tired in different places perhaps, but they're not actually doing less work in the system. Now you can, this next area is going to take a look at some of our the shapes of our initial scientific designs in our studies. This was the first sort of prototype, and yes, it accomplished the task, but it's not something anyone would wear. Here's the second design prototype as we were in the lab. You'd never wear that either. This one was never ever got off the drawing board. This was one of the ones used in the fatigue study. So you can tell by that none of these would ever be worn by a worker. They're just too ugly, so to speak. Let me get out of here. Okay, there we go. Okay. So what we started working on next was trying to get a system in place that could possibly be manufactured and given to the workers. So the different system then is you still need, it's a lot of force that you're taking off the back. So you still need anchor points if you're going to stretch a spring, and one of them is going to be underneath the feet and the other one's going to be on the shoulders. And so we're now starting to take a look at different designs that might actually accomplish, what we need. And so our first one of getting out in industry was this one, where again you have a strap underneath the shoulders, the cables are protected inside, there's a pelvic spacer right here to give you a better moment arm for those elastic elements, and then the other anchor point is the shoulders. So that's the first prototype that went out into the field. And so we tested in an automotive company. They did a 2-hour task, 25 seconds worth of work, 30 seconds worth of rest was a cycle of putting in this left-hand dash task. So the people wore, we tested them with and without the device. We also tested, so we had EMG as well. We also had an accelerometer so that we could verify that posture wasn't the reason for the change. It was going to be the device that would be the reason for the change. And we took a look at some pre-post questionnaires as well. And so here's your EMG data, again, looking at the differences between, this is the thoracic area, the lumbar area. Here's your PLAD in the blue. And you can see, again, we were reducing the level of activity. And the workers could actually feel that as well. EMG was reduced by about 20%, and 8 out of 10 workers said that they would wear it for similar jobs. Some jobs would not be appropriate, and so they would wear it for the jobs that were appropriate. Sorry. It is. Okay. All right. We then were taking a look at different, I won't go into this one very much, but we were trying to take a look at different tensions and what people would prefer as a tension in the system. So we were doing that. We then went out to a number of different industries, having them wear it. This was also part of the design process. We were changing the design as we were going out to industries. And so we had 6 different industries. We had pain and discomfort ratings. We had subjective ratings on whether or not they thought it would be effective and so on for them. And as I say, we initially had it inside a pair of pants. We then started working in terms of getting it outside the pants, which would be acceptable for some industries. And so that's more or less a look of the recent design at that point. In terms of some of the results from the field, the workers that wore it perceived that it would be 60% help. We pretty much know it wasn't 60% help. You would have to use your abdominal muscles to get down to lift if it were 60% help. So it really is around 25% help, but you feel as though it's like 60 or 56% help. This is true here for lifting to waist height or lifting and lowering from floor height. They also found it effective at waist height. This is a false reading. The PLAD is not effective at all if you're going to lift overhead. You're not even invoking the assistant to part. Bending forward, definitely a lot of help for jobs where a person is having to lean forward in a sustained posture. And then just one of do you believe it's effective? And yes, they believed it effective. As we were going through, they were concerned sometimes about heat when you're wearing the particular pants, and some people just didn't like the design of the pants, so I mean, that's one of the problems. Getting the appropriate stiffness and coming up with a simple donning and doffing approach was necessary. So in terms of its effectiveness, we believe that we have proven that it is effective in terms of reducing moments, fatigue, and back muscular activity. It also changed the lifting technique, but if you put it on, you can feel it until your body gets adjusted to it, and when you take it off, you feel that as well until your body gets adjusted to it. So it adjusts very quickly to what you're doing. And in terms of acceptable to the worker, it did not affect their physiological demand. The workers actually could tell it made their legs work harder. They knew that, after wearing it for 4 hours. And they really could feel that it provided assistance. And 66% of the workers said they would wear it, even in its current design iteration. So the design iteration has continued to improve, and we're pretty close to being market ready at this point. So thank you very much.